Here is a presentation of my thesis called Kubernetes Scalable Deployment for Brain-Computer Interface Machine Learning. Here's what I'm going to be talking about: the introduction and the problem, the solution architecture, testing results, conclusion and future work, and then question and answers. Here is what the Avatar project is about. It's an open source brain-computer interface research project at St. Cloud State University, and we use open BCI headsets to capture EEG signals from brainwave activity. Currently, we have over 4,000 brain readings that have been captured. We then use a machine learning model to train this data so that we can interpret thoughts in real time. The trained model is then used to convert thought patterns into drone and robot commands, such as takeoff, forward, backward. Here is an example of the EEG headset being worn, and here is a picture on the right showing the EEG data stream that is gotten from the headset. Now, for my thesis, the problem was that deep learning for BCI is computationally intensive, and most students and researchers don't have high performance GPUs on their computers, and they often have low system specifications. And so model training is really very slow. Also, there is no directly accessible centralized storage for EEG data used in model training. Everyone has to duplicate the data themselves. And also, collaboration is limited and results are difficult to reproduce. The goal of the thesis was to deploy and evaluate a Kubernetes-based infrastructure to provide access to shared GPU and CPU resources and centralized data management for collaborative BCI machine learning research at St. Cloud State University. The objectives of the thesis were to develop a Kubernetes cluster with one GPU master node and two CPU worker nodes, to deploy Jupyter Hub to provide secure multi-user browser-based notebook access, to implement NFS-backed persistent storage for centralized EEG datasets, to enable SSH access for secure remote connectivity, and to evaluate performance by comparing the CPU and GPU model training speed and accuracy. Now, for the architecture that was used to achieve this, Kubernetes was used. Kubernetes is an open source orchestration platform that is used for managing containerized applications. It essentially consists of a control plane and the worker nodes. And this Kubernetes provides load balancing, resource management, and self-healing capabilities. In this project, we use Kubernetes to manage all the Jupyter Hub user pods and automatically allocate CPU and GPU resources. Jupyter Hub is a multi-user platform that is built on top of Jupyter Notebooks, and it manages user authentication, session creation, and resource isolation. Every user that logs in gets a dedicated notebook server inside a Kubernetes pod. It also allows browser-based access and essentially prevents any installation that will be needed on a local machine, and is also very ideal for the Avatar project, because the Avatar project is a research project. Now, network file systems was also used in the architecture, and NFS is a protocol for sharing files over a network and allows multiple users to access the same files as if they were local. In this project, we used NFS to provide centralized storage for EEG data and user workspaces. We also used it to enable persistent volumes in Kubernetes, which ensure that data remained even when pods were deleted or moved. Now, for the Kubernetes cluster architecture, we created an on-premises cluster, which was deployed across 3 physical servers in the BCI lab. We had 3 nodes. One was the control plane, which was the master node, and was set up on a high-spec NVIDIA GeForce RTX 4070 GPU server with 125 gigabytes of RAM. The worker nodes, 2 in number, were had just 12 gigs of RAM and were made to handle lightweight CPU workloads. The NVIDIA device plugin was also installed on the master node. Now, we installed Container and Calico Net for networking. We joined the worker nodes to the cluster. The NVIDIA device plugin was also installed on the master node so that the containers could have access to the GPU, and the GPU node was labeled for workload scheduling. Here is a screenshot that shows the partial result of the kubectl get nodes command, showing that showing three nodes and showing the statuses of the nodes. Then we went on to deploy Jupyter Hub via Elm charts. We set up server profiles for users to choose from a CPU server profile or a GPU server profile. We also isolated user ports through Kube Spawner, which was automatically handled by Kubernetes, and also created simple browser access for students. Here we see a user pod named Jupyter Workstation 1 created for a user. Here is also a screenshot showing the login page. This shows the loading process when a Jupyter Hub instance is being spawned for a user. Here is also the server profiles that allows the user to choose between a CPU and a GPU server. This is the Jupyter Hub environment that has been spun up for a user that allows them to run their Jupyter notebooks and train their models, in their browser remotely. Now for the persistent and shared storage configuration, we set up the NFS server on the master node and ensure that Kubernetes had access to it. We also created PVs and PVCs, which 50 gigs was allocated for shared data on the master node, around 50 gigs or 30 gigabytes. We also had 10 gigabytes set up for users. Then we had shared data that was saved in the shared data PVC. Every user also, was configured to receive 10 gigabytes PVC, and that ensured that even after the user logged out or deleted a pod or a pod was restarted, the user's data remained intact. Here's an example of the shared data PVC and the data that was actually stored in there. Now for the results, we're going to be considering the environment in which the project was run. We used a master node and two worker nodes. Here are the processor specifications and the processor memory and GPU specifications for each of them. Also, we ensured that the GPU was visible to the notebooks that are being run, the Jupyter notebooks, and running this command, we actually got the confirmation. Now, here are the average CPU results for time and accuracy. For the CPU, which are the worker nodes, for the TensorFlow model, which is a Jupyter notebook that is currently existing in the Avatar open source database. TensorFlow model at a mean time of 1105.86 seconds and a mean accuracy of 99.76. PyTorch model, which is also available in the open source Avatar project, had a mean time of 967.84 seconds and a mean accuracy of 98.65 seconds. For the GPU node, which is the master node, when running the TensorFlow model, we had a mean time of 88.18 seconds and a mean accuracy of 99.73 seconds. For the PyTorch model, we had a mean time of 496.10 seconds and a mean accuracy of 97.92%. For the average training times for both of them when put together, the CPU had an average training time of 1036.85 seconds and an average accuracy of 99.21%. The GPU had an average training time of 287.14 seconds and a mean accuracy of 98.83%. Based on all the data, here are the key findings. On average, TensorFlow and PyTorch achieved comparable accuracies on both CPU and GPU, both consistently above 98%. The CPU training times exceeded 15 minutes per run on average, which demonstrates limitation of CPU-only training for deep learning workloads. TensorFlow consistently achieved shorter training times and slightly higher training accuracies on GPU compared to CPU. PyTorch also benefited from the GPU acceleration. Also, the GPU training was approximately 3.6 times faster than CPU on average. And even though accuracy remained consistent, the significant reduction in training time emphasizes the effectiveness of GPU acceleration for deep learning tasks. The results confirm that while CPU resources can achieve nearly identical accuracy, they are inefficient for iterative model experiments or time-sensitive workloads. Yeah, so we testing the usability test, the test the login and notebook access that was passed, the GPU test also, which was to confirm the availability of the CUDA, which is essentially the layer that allows the notebooks to utilize the GPU, was also passed. The NFS persistence test also passed, as we'll see in the demo. Future work includes scaling the cluster, adding more GPU servers, advanced scheduling to implement resource quotas, enhance user management, and extending the platform to other AI projects at Singlehurst University. Thank you. We will now go and have a demo to um to show what we currently have. Currently the cluster is set up with two nodes active, one GPU node and one worker node. This worker node is identical to the other worker node. So we just have two instances, the GPU node and the CPU node. When we attempt to get the namespaces in the cluster, we see we have several namespaces, networking namespaces, the default namespace, a couple other ones that are needed for the cluster to work fine as well. We have the GHub namespace, which is the one we're going to be working with, which is the Jupyter Hub namespace. We also have the NFS namespace. To see the pods in all these namespaces, we see that there's several pods in namespaces. The Jupyter Hub also has its default pods as well. Now we're going to go into the Jupyter Hub namespace, and we can see all the names, all the pods that are currently under the JHub namespace. Um, we can also check the PVCs, the persistent realm storages. That's the file storages under the JHub namespace. Here we have this, which is 1 gig in capacity, and we have the shared storage, which is 30 gigs in capacity. The shared storage makes data available to every single user of the Jupyter Hub namespace. Now, to actually use this, namespace, let me go on. To use the namespace, to use Jupyter Hub, I have already carried out port forwarding, SSH port forwarding, to be able to use and access the Jupyter Hub port. Let me just hide this. Okay, so to be able to use this, I carried out SSH port forwarding, which means I'm currently connected to the Kubernetes cluster, and I have access to Jupyter Hub on localhost. So I will just go ahead and create an account. So this is exactly how students are expected to use it. I will just call this workstation. Let me just call this worker1, and then use the default password that has been assigned for the cluster. Now I'm presented the option to select a CPU notebook or a GPU notebook. I will just go ahead and use a GPU notebook. And then an environment is created for me, a Jupyter Hub environment is created for me, one which is assigned to the master node because I selected GPU. And if I run this command again, I see that a pod has been created for me called Jupyter Worker1. If I also run the PVC command, I see that a PVC with a capacity of 10 gigabytes has been created for me, a PVC, a persistent value claim. Now, in the event that I log out, which we're going to see, my data is actually going to remain intact. Now I have access to the shared data. The shared data ensures that I have access to ensures that every student that uses this environment has access to read-only shared data, meaning I cannot modify this data. So I'm just going to go ahead and copy this from the shared data into my own environment. and open it up. And I'm going to go ahead. I can actually run this. I can run this model. Let me just do share data. Then I have access to mini data. I can go ahead and run this Jupyter notebook. I cannot modify the ones that are in share data, but I can use the data. I don't need to copy the data into my own environment, and I can go ahead to run this. And this gives me everything that I need. Can go on to run the notebook and actually install everything that I need to install and train my models. Now I can also log out, and in the event that I log out, let me go to the control panel and stop my server. Now that I've stopped my server, when I go back, I can see that my pod has been destroyed. But when I check my PVC still remains there, which means that if I actually go on to log in again, even if I log in to a different, even if I decide to use the CPU this time around, all my information is still there. It's still preserved. So students can then run their models remotely and train their models and their Jupyter notebooks on the lab computers. And that way they have access to all the GPU resources and the CPU resources that are present in the lab. And so they can collaborate, they can share information, they can have access to centralized data, and they can train models faster and more effectively for the Avatar project to be more, to have better research and progress at a faster pace. Thank you.